Welcome everyone to the first DGraph seminar of the semester. And my name is Kent Yagi at the University of Virginia. I'm chairing this seminar today. I'm really glad to have two speakers from Nanograph today. The first speaker is Javi Siemens at Oregon State University. And he's currently the PFC co-director of Nanograph. And he received his PhD from Tufts University in 2002, then did postdocs at the University of Wisconsin-Milwaukee and Caltech. And then he came back to UMW as an assistant professor. He got promoted to associate professor there. And then he moved to Oregon State University as full professor. Our second speaker is Joe Simon, and he's a postdoc at the University of Colorado Boulder. He received his PhD under supervision of Javi in 2017 at UMW, and then he did his first postdoc at JPL, and he's now at University of Colorado. Let's see, we will have Q&A session at the very end, so please hold on to your questions, or feel free to write your questions on chat during the talks. And let me also remind you to please abide the APS code of contact. Okay, without further ado, let me give the floor to Javi.
Great, thank you for the kind introduction, Kent. Yeah, it's a pleasure to be here. We're going to talk about a recent set of papers that we published in late June of this year, where we presented multiple lines of evidence for a stochastic background of gravitational waves in our 15-year data set. Nanograph is a collaboration of about 200 students and scientists or so, mostly working in the US and Canada. What we're trying to do is to study the universe using low frequency gravitational waves that we can detect using pulsar timing arrays. And we're part of a worldwide effort, which includes folks in Europe, Australia, India, China, and South Africa. And we all form a sort of Uber collaboration called the International Pulsar Timing Array. In the US, we are very fortunate to be funded by a Physics Frontier Center, which we first got in 2015, and then renewed a couple of years ago in 2021. So our experiment, our gravitational wave experiment, is complementary to all other experiments that probe the gravitational wave spectrum. I'm sure all of you know about you've all heard about the LIGO detections, the LIGO-Virgo-Kager detections. I think these days it's about 100 or so binary systems that have been detected. Not 100% sure, but it's plenty. And we want to probe different parts of the gravitational wave spectrum, because that gives us access to different astrophysics. So LIGO and Virgo are sensitive to gravitational waves from binaries with component masses between several tens of solar masses, whereas we are sensitive to binary supermassive black holes, so billion solar mass black holes, along with a plethora of other kind of more speculative sources, things like cosmic strings, phase transitions, primordial black holes, and also inflation. And of course, there are other experiments going on. The cosmic microwave background experiment that tries to detect the primordial spectrum from inflation using the polarization properties of the cosmic microwave background. And then LISA, which is a planned experiment for the 2030s, is in the works as well. Our detector works with two components. The first component is a type of neutron star called a pulsar. So pulsars have strong magnetic fields, spin rapidly, and emit beams of radio waves from their magnetic poles. And if at any point in the rotation the magnetic pole is pointed toward Earth, then we observe these pulsars like sources of bursts of radio waves. And we effectively use these like clocks that are spread out throughout the galaxy. These objects, so neutron stars and pulsars specifically, are very interesting. They are city-sized objects with about 1.5 to 2 solar masses, so they have nuclear density, magnetic fields that are billions of times stronger than what we can make on Earth, and they spin faster than a kitchen blender. Right, so these are very exotic, very interesting objects in their own right, and they are a laboratory for nuclear physics. That is also, so there's a lot of synergistic science that we produce along the way in our study of gravitational waves that also is very interesting. The second component of our detector is radio telescopes. So we use the world's most sensitive radio telescopes. We point them at our pulsars to measure times of arrival of these pulses. And up until 2020, we were using Arecibo, and our latest data set includes 15 years of data from Arecibo. After Arecibo collapsed, we moved most of our pulsars to the Green Bank telescope. The Arecibo telescope was the largest and therefore the most sensitive because it had the most collecting area. This is 300 meters across. And the Green Bank telescope is only 100 meters across. This picture really doesn't do it justice. It's the size of a football field and it's fully steerable. So we can get very sensitive data from this time of arrival data for the pulses from the pulsars using this radio telescope. And more recently, we've also been using the Very Large Array in New Mexico and the Canadian Hydrogen Intensity Mapper experiment in Canada. I like mentioning this. I like talking about these two pieces of our detector because the fact that we can you build a radio telescope, point it at a pulsar or point it at a set of pulsars, and use that as a giant sort of galaxy-sized gravitational wave detector. I found it such a compelling and beautiful idea about 16 years ago that I just had to start working on this stuff because I thought it was just very beautiful. And we're really fortunate that nature has gifted us these objects that all we have to do is build a radio telescope, point it at them, and we have a gravitational wave detector. So what we do to summarize is we observe an ensemble of pulsars that are spread out throughout the galaxy, and as gravitational waves pass through the galaxy, they stretch it and they squeeze it. They make the times of arrival of these pulses arrive a little bit earlier or later, depending on what the gravitational waves are doing. And that is the effect. And they do so in a correlated way, which I will explain in a second. And that's basically our gravitational wave detector. This animation, by the way, was put together by folks at NSF, and these actually represent the actual locations and as far as we can tell, as far as we know, the distances to the various pulsars that we use for the 15-year data set. The most promising sources in our band, in the nanohertz band, are supermassive binary black holes. These form when galaxies merge. The galaxies host supermassive black holes at their centers. When galaxies collide, and we think they grow by collision. So galaxies grow by collisions through the history of the universe. So whenever these collisions are going on through the history of the universe, the black holes at their centers will meet, orbit around one another, and emit gravitational waves. And those are our most promising sources. The final merger of the two supermassive black holes emits a burst of radiation, which in our data, in our time of arrival data, looks like a ramp. Earlier on, when the two black holes are further apart, they're emitting sinusoidal waves that are shown here in the middle in green. And the sum of all the continuous waves, all the individual supermassive black holes that are merging, form a stochastic background of gravitational waves. And that's the most promising type of signal that we expected to be able to detect, and what we have evidence for right now that we'll tell you about shortly. There are other sources at nanohertz frequencies that are, like I mentioned earlier, they're more speculative, things like cosmic strings and phase transitions, primordial black holes, inflation. I don't think inflation is as speculative, but there are other more kind of exotic sources as well that are emitting gravitational waves in the nanohertz band, and we look for those as well. So as I mentioned, what we do is we measure the times of arrival of pulses from pulsars, and that amounts to keeping track of every rotation that the pulsar does over many years. We construct a timing model, something called a timing model, that we use to predict when a particular pulse from a pulsar will arrive at our radio telescope, and then the difference between that prediction and the actual time at which the pulse arrived is called a timing residual. Basically keeping track of every rotation is. So I want to write this equation because I'm going to use it later later on in the slides. But we're effectively keeping track of a phase, right? The rotational phase of the pulsar. And since gravitational waves, change the distances between the pulsar and the Earth, they change the light travel time between the pulsars and the Earth. They're going to change that time of arrival, so we can try to look for gravitational waves in this timing residual data. And what gives us the sensitivity to really probe gravitational waves, which are very tiny, is that we can predict the arrival times to our best pulsar from our best pulsars to about tenths of nanoseconds over many years. As I mentioned, we're the kind of smoking gun for gravitational waves is a correlation pattern. So when you take two pulsars, say that are separated by a small angular separation here on the left, we have a positive correlation. When they're around 90 degrees, we have a negative correlation, and at 120 degrees and above, again, we have again a positive angular separation, and we want many pairs, right, of these pulsars. So here's a picture of one pulsar, and all the pairs that it has with all these other pulsars, and we want as many pairs as possible to try to populate as many of the angular separation bins on this curve as possible. That's what gives us the
Did we lose Javi?
I think so.
Okay, or maybe we can wait a bit to see if he comes back. Now we lost him completely, and let's hope that he comes back.
Well, we have two speakers, so
Yeah, if he doesn't
Joe.
come back in 1 or 2
Yeah,
minutes.
if he doesn't come back, I can
Yeah.
I can jump in, but
Mhm. Maybe
Like
let's
tag team. This is the tag moment.
yeah.
let's wait for 1 minute, and then yeah, if he doesn't show up, Joe, you can take over.
Maybe we can advertise the next seminars. It will be November 2nd by Sam Grala, Ahonji Weeb. And then the next one is December 7th by Alessandra Papa and Benjamin Stein. So stay tuned.
Thanks, Alejandro.
Do we have more announcements?
The recording of today's talks will be available on YouTube channel, and the link will be available through the DGrav seminar website. Yeah, maybe it's best if Joe, you start sharing your screen and then take over.
Yep, I will do that.
Thanks.
All right, let me do that here. I don't think we have. Let's see, where was he? He was back there. Okay. 1 second to pull up the slides. And go ahead.
So for the people that are joining right now, we lost Javi.
Oh, he's back. He's
folks,
back with me.
sorry,
Okay.
sorry I dropped out.
Oh, I see. But he has to
Can you all hear
rename
me?
himself. Yes.
I do. I'm sorry. Let me see.
Okay, I just rename you. Yeah. Good.
I am very sorry, folks. I'm actually using my cell phone as a hotspot. Flatiron just fell over here. So I won't share. I won't turn on my video just in case that screws up the thing. All right, can folks see my screen?
Yes, perfect.
Yep.
Oh, okay, great. I kind of forgot where I dropped off. I think I will just did you all see this slide, or was I already gone by the
Yeah,
time
we
you
were
saw
here.
this?
You were just mentioning I have here a pulsar and I want as many as I can have.
Right. Okay, perfect. Okay, I will just continue. So let me again, very sorry about this. So let me talk a little bit about the models that we use to detect in our searches, right? So I said many pulsars, 67 in our latest analysis. So each pulsar in this figure here has Bach and has its own timing model. As I mentioned, we try to fit we try to predict the times of arrival using all kinds of where the pulsar is in the sky, its rotational frequency, its spin down, etc. So each pulsar has a timing model, some white noises and a red noise. And these are all intrinsic to each pulsar. And then we also have a common process, which is a common signal across pulsars, which is possibly correlated. We do is actually we do all of this simultaneously. We marginalize over all of the intrinsic pulsar pieces, the timing model, the white noise and the red noise, and we search for a common signal across pulsars, which is possibly correlated. And the reason we do that is because we expect that meaning possibly correlated, is because we actually expect the stochastic background to show up first in our data as a common red noise process. And then later, as we take more data, as we add more pulsars, we can extract the correlations, which are actually weaker than the intrinsic, than the common red noise signal that we have. So I wanted to summarize real quick some of the our results from the last few years. So for the 5 and the 9 year analyses, we actually had just upper limits. So we didn't detect anything. The pulsars look very white. We didn't detect any common red noise process at all. And so all we did was set upper limits. The first time things got exciting for us was in the 7-year data set. There, our first analyses actually did yield a common red noise process. And what I mean by that is a red noise process at the same amplitude and spectral index across pulsars. And of course, we worked really hard to make that go away, as we should. And in the end, what we found out was that that red noise process, we could actually make it go away by using different versions of something called the solar system ephemerides. So to remember that I mentioned that we are track of every pulsar is basically keeping track of the rotational phase. In order to get an equation like this for the phase, we need to pick an inertial frame. The inertial frame that we choose is the center of mass of the solar system. In order to calculate that, we need to know where all the planets are and where all the solar system objects are, the sun and the Earth, and all the planets, etc. All the objects in the solar system. We need to know where they are and how much mass they
Okay, lost him again. Oh, he's back. Abby, are you there? Can you hear us?
Okay, I can hear you. Yes, but I was muted for some reason, so I'm sorry about that. And I'll share my screen again. I'm very sorry about all the technical difficulties. By the way, folks, this is a lot of time on Zoom, so as you can imagine. All right, so yeah. So I think
we are not seeing your screen yet.
I am not sharing my screen.
I think it is
right.
trying.
Let me see if I can. Yeah, maybe, by the way, Joe, when it's your turn to give a talk, maybe you should do the sharing. And so because my internet is very flaky today for some reason. All right. Okay, how is that?
It's trying. It says you've started screen sharing, but now we see your screen.
Okay. All right, very good. Very good. Okay. Yeah, I think where things look like they went wrong was when I was talking about the keeping of the rotational phase and how we need an inertial frame for that. And in order to calculate that, that's the center of mass of the solar system. And what we found using different ephemeris, and that's what's shown down here, so we would get different results for that common red noise process. And so we went, aha, well, that's the problem. And so what we did, and it turned out the culprit was actually Jupiter, like where the orbital parameters of Jupiter, there were many different versions of the ephemeris that were giving us different results, and include that, well, timing, all the noises and all that, everything simultaneously, including the orbital parameters of Jupiter. So solving for the whole. That's when that made actually this thing go away, and it was really fun. I wanted to. It was really fun work, and I wanted to say that the differences between the different ephemerides versions that NASA puts together in the actual location of the solar system center of mass was 100 meters. Okay, this was very, very, very small changes in the actual thing, but we were sensitive to that even at that point. The next paper was
All right.
okay.
Oh.
All right. Well, I'm almost done here with my part of the talk, so at least there is that. Okay. I just, this is one more slide, and then Joe will share, and then hopefully it will be okay. All right. Right. So this paper was led by Joe Simon, and what happened with the 12.5-year paper was that we actually again found a common red noise process. And this time we also worked really hard to make it go away. And we spent several years trying to make this red noise process go away. And we could not. Of course, we tried the ephemeris, like we had the 12, maybe it's the ephemeris again, or maybe it's something else. We tried many, many, many different things to try and make this red noise process go away. And we could not. In the end, what happened, so this was the plot that we showed. Here's the common red noise process in orange or blue. And that corresponds to each pulsar has its own intrinsic parameters and then a common process, which is the same amplitude and spectral index across pulsars. And that's what we showed here. And we detected this to very high significance. There were no significant correlations. But anyway, like I said, we spent a lot of time trying to make it go away, but we couldn't. In the end, what happened was that we asked a couple of people in Nanograph to generate preliminary data sets for the 15-year, preliminary 14 and 15-year data sets. And then Joe was the first person to see this, actually. We actually detected some weak correlations in these data. And so we went, phew, okay, this red noise is it's actually gravitational, or so we thought. And so we went ahead and published the paper, but it took several years for us to actually get to where we were comfortable. Turned out not to be sort of a new systematic in our data that would have been really detrimental to our experiment. All right, so the next set of slides are for Joe, and I'm going to stop sharing, and then hopefully the disaster will not be continued here with my horrible back.
No worries. All right. Can everyone hear me and see my slides?
Yep.
Yes.
Wonderful. Awesome. All right. Well, thank you, Javi, for that that introduction. And yeah, so I am also very excited to be here and to be talking with you all about these results. Give me 1 second. I actually don't think I have the updated slides pulled up here. Yeah, I apologize. Here, just give me 1 second. Okay, look at this, and then I will do this. Oops, wrong one. All right. Okay. Share over there, and off we go. All right. So as Javi was saying, so we had we saw a strong uncorrelated process in our 12.5-year data set. In the 12.5-year data set itself, we did not have evidence one way or the other for these sort of telltale cross correlation signatures. And so that brings us to the 15-year where we do actually have evidence for the cross correlation signature that is indicative that this common red process that we've been seeing really for multiple data sets now, the hints of it have been in there. We just haven't been able to say what exactly it is. And so now, accompanied with evidence, we can say that it is very likely a gravitational wave background. So one of the ways that we sort of do this is we use different Bayes factors or odds ratios to test various models against each other. And what we're doing here is we're setting up a series of sort of nested models where the base model stays the same and we just test sort of one more additional piece. Our base model is one which includes just the noise terms for each individual pulsar. This includes their timing model, their white noise terms, and their red noise. And we just have only those signals for each pulsar individually. That's our sort of base of there being no common process. Now we compare that model to a model where we just add an uncorrelated common red process. So this is the signal that appeared in the 12.5 and in the 15 year data, what we see is that the presence of that signal is even more significant than it was in the 12.5 year. So there's overwhelming evidence that there is some sort of a common spectrum process in our data set. And then the additional piece that we're testing is whether or not that common process has the cross correlation signature of a gravitational wave. And that's not the only correlation signature that we test, but that's the only correlation signature that comes out with significant evidence or a very large Bayes factor in favor of that model. And so depending on how exactly we set up those models, we're seeing Bayes factors of a few hundred up to 1,000. And all we've done here is take our model with a common process and just asked, does this common process have the cross correlation signature that is expected for a gravitational wave? And so that's what this model is here. And that's what we have positive evidence for. We test some other correlation signatures for a monopole or a dipole, and all of those we are very favored against them. So it's not just that we have some correlation signature and we're not quite sure what it is, but it truly is that the correlation signature that we are seeing is the one expected from gravitational waves. And so this is from our actual data. The blue is the cross correlation terms from the 15-year data set. And the black here is what is predicted from gravitational waves. And it was first published by Hellings and Downs. It's called the Hellings and Downs curve. That's where this HD comes from. And so how do we assess the significance of these numbers, though, right? A Bayes factor of a few hundred, what does that actually mean? And so what we're able to do is we're able to construct a series of different sort of null hypotheses, right? So sort of we're able to break the correlations through phase shifts in the Fourier bases, and when we do this, we find the significance of our signal, of the correlation piece, that uncorrelated noise alone would produce a result, you know, sort of a 1 in 10,000 or so chance, right? So in terms of like sigmas, it's somewhere between 3 and 4. And we've done a series of different validation tests, right? We've split up our data set based on telescopes, based on backends. We have done everything that we can to sort of get rid of this signal and to think, what else could it possibly be? And none of those have really revealed anything other than the gravitational wave signature that is in our data stays. So I'm going to switch a little bit and start sort of talking about, okay, what is the signal that we're seeing? What is the power spectrum? What can we actually do with that? And so to be able to understand that, I'm going to talk a bit about sort of where the spectral characterization constraints in our data set come from. And so in our correlation matrix, right, sort of the gravitational wave background is the only thing that is cross-correlated between pulsar pairs, or it's the only thing that we know of. So the cross-correlation channel is a very clean signature. The auto terms, right, that's where all of the other sort of noise properties exist. So all the white noise terms, all the red noise terms, and there's the ability to have some interaction between the pulsar intrinsic red noise terms and the common gravitational wave background signal. This is something that we've studied very extensively, particularly after the 12.5 year. There were a lot of tests to really try to understand what's the relationship between the intrinsic red noise properties and sort of the uncorrelated common process piece. However, those auto terms are much, much, much larger than the cross terms, right? That's why they showed up first. And that's why they continue to sort of dominate our spectral characterization. So our ability to constrain the power in the gravitational wave background is really sort of reliant on how well we can disentangle that common piece from the intrinsic noise properties. And as I talked about a few minutes ago, the common uncorrelated spectrum, right, that auto term, right, we have overwhelming evidence for that process. And it's only a comparatively smaller step for that process having the gravitational wave cross correlation signature. And so while we do filter the signal by demanding it to have that cross correlation feature, those cross correlation terms are much smaller than 1. And so that additional bit of information is still relatively small compared to the overwhelming amount of information that we get from the auto terms. And those auto terms are still sort of subject to interaction with the other noise model terms. So our spectral characterization is still really dependent on how well we can model all of the rest of our noise. And unlike other experiments, we can't just walk out to a pulsar and sort of jiggle it and sort of see how it responds. So we are fitting these noise terms simultaneously to our fits to the background. And so that sort of makes this process inherently a little bit trickier. And so here I'm showing from the 15-year data, the power from the background as a function of gravitational wave frequency. In the 12.5-year data set, it was really only the lowest 2 or 3 frequency bins that had any power. Here, we're seeing consistent power up through, sort of the 8th or 9th frequency bin. And here I'm showing both the power that you get when you just look at the uncorrelated piece, and that's shown in the blue and on the left-hand side of the violin plots. And then when you filter by sort of requiring HD correlations, that gravitational wave cross correlation signature, that's being shown in the orange on the right. And what you can see is that they generally agree, but they don't exactly agree, right? And so what we're seeing is that common uncorrelated piece, there's still some other sort of intrinsic properties that are sort of finding their way and interacting on those auto terms. So so even once we filter by the Hellings and Downs correlations, because that's such a smaller term, we're still not having a perfectly clean channel. And so sort of the spectral characterization that we're finding is really sort of noise model dependent. We still have that piece, and we're still at very early stages of really characterizing the power and understanding what this signal actually is. Now, broadly speaking, it is consistent with predictions for a population of supermassive black hole binaries, right? That's shown here in the dotted line. That's sort of what you would generally expect a population of supermassive black hole binaries to produce a background with a power law at a spectral index of roughly 13/3. Now, the best fit power law to the data is slightly shallower than that. There's a lot of sort of reasons for that. It tends to be that the lowest frequency bin is a little bit sort of lower power than you would expect for just a pure 13/3 power law. And there are some frequencies at higher, there are some of the higher frequencies where there's some power that's a bit above that. Now, we're still sort of investigating that, but the general takeaway is that this process is really sort of broadly consistent with our expectations. And this is true for all of the other potential gravitational wave source models that Javi talked about earlier. But I do really want to caution, right, that sort of the spectrum that you see now will definitely not be the exact spectrum that you will see in the future, because as we are beginning to better understand all of those intrinsic noise processes, it's easier to sort of isolate them from the common process. And as the significance for the cross correlations continues to increase, the ability to really filter the gravitational wave background from everything else will really improve. So with that being said, let's talk about what this could actually mean. So I think one of the most exciting things is to think about what is causing this gravitational wave background, and what can that tell us about what's happening in the universe, right? This PTAs are a very unique probe of the universe. So what can we use this data to sort of learn about what's happening in the universe? So I'm going to start by just talking about binary supermassive black holes. It's really cool that our sort of most blasé vanilla model is the cosmic population of binary supermassive black holes. Like that's the like ho hum signal. But so here there's I'm showing two different sorts of models for the supermassive black hole binary population. The orange is just showing sort of what happens if you just evolve with gravitational waves, and the blue is if there's some amount of interaction between the binary and the galactic environment. On the y-axis here, sort of more towards the top, that's predicting sort of more massive systems, more numerous systems. And then on the x-axis, it's sort of more interaction, less interaction. And you can see sort of where the 15-year data sort of lands. And it's more towards sort of the higher end, and perhaps more towards things potentially interacting, continuing to be coupled with their environment as they enter the PTA band. So again, it's sort of tentative at best, but the first hints are really, really interesting, because there's this sort of common question of in the local universe, right? We see supermassive black holes that have a mass that correlates with some other property of their host galaxy. And the question sort of is, did they evolve over cosmic time in step? Did the galaxy grow first and then the black hole caught up, or did the black hole grow first and then the galaxy caught up? And so the first hints that we're seeing that perhaps supermassive black hole binaries are more massive or sort of more numerous than we expected, it's actually starting to sort of be consistent with some of the emerging pictures from JWST, which is very exciting and means that sort of these systems have potentially evolved a lot earlier, and there's a lot more of them than we first sort of thought. The other thing that we're seeing is, if in fact this is from the population of binary supermassive black holes, then there is no final parsec problem. And for the most massive systems, they evolve relatively quickly through the sort of binary hardening phase. And so that has really sort of big implications for sort of the multi-messenger signatures and the science that you can get out of them. All right, we are running out of time. I've got a lot more to go, so I'm going to speed up here. But there's so many other really exciting sources out there. I think there have been a few hundred different papers that have been put on the archive in the last 3 months explaining what this signal could be. Things from inflation to scalars to first order phase transitions through cosmic strings and domain walls. I mean, just all sorts of awesome things. And it's really cool to see all of the interest and all of the excitement in trying to understand and explain what this signal could be. And I will say that as of right now, there is nothing in our data pointing to what the source of this signal actually is. That continues to be a big open question. So here I'm just showing a couple of different models. The gray curves here on the left side of the plot are the actual NanoGrav 15-year data. The colored curves here are a bunch of different models. As you can see, depending on your sort of favorite inflation or cosmic string model, there's some area of parameter space that can be found that sort of fits some portion of our signal. I think one of the cool things is thinking about the sort of multi-band constraints that can be placed on these signals. So here are upcoming and sort of other ground and space-based instruments and their sensitivities. One of the really cool things is, if this is in fact cosmic strings, there are some cosmic string models that will completely swamp all of the LISA band. So once LISA turns on, it's just going to be cosmic strings all day, every day. So that could be cool. But as I said, there's no strong conclusive evidence sort of one way or the other. So here we did a lot of testing of sort of these new physics models compared to just a supermassive binary black hole population power law. And then you can also compare the binary power law to the new physics plus the binary power law, right? So that's what all of these different Bayes factors are. And the takeaway here is that there's no conclusive evidence sort of one way or the other. There's tons of uncertainties in all of these models. All of these base factors, right, are sensitive to your prior choices. And as I said earlier, they're very sensitive to the specific noise model that that you included. So again, depending on the spectral characterization, lots of things can sort of change. But there's a ton of unexplored space here that's incredibly exciting. And so what can we do to actually start to maybe pinpoint the source, to start to pick apart distinguishing between what is the primary source that's contributing to the background? And so the first thing that we can do is we can look for anisotropies in the signal. So instead of just looking for power in a specific gravitational wave frequency, we can also search for gravitational wave power across the sky. And if the background is coming from a discrete population, such as binary supermassive black holes, then we expect the anisotropy level to be much higher than if it's coming from some cosmological source, right? Some byproduct from inflation. And so this is one of the first places that we're starting to probe and sort of really think about the gravitational wave background power, not just the spectrum, but also the power distribution across the sky. While there's no evidence for anisotropy as of yet, there have been predictions that sort of point to within the next 5 years or so. So this really is the next horizon, and it's worth sort of noting here that our ability to constrain anisotropy is best where we have sort of most of our pulsars, right? So all the red dots here are the pulsars in the 15-year data and sort of where they are on the sky. The blue here is setting the upper limit on the level of anisotropy across the sky, and certainly we're seeing that we're able to probe that significantly better where we have the majority of our pulsars. One of the other things is that if there is a discrete population, then there should be individual systems, right? Continuous wave sources that should sit on top of the background. We're also searching for those. Again, we don't find any. One of the really cool things is that you need to simultaneously model the background and these individual systems at the same time, or else you can have this individual system models sort of pick up hints of the background. So there's an interplay there that you need to be careful for. Again, our constraints are sort of dominated by where our best pulsars are on the sky. There's a ton of interesting binary black hole candidates, and so we can do targeted searches, put individual constraints, specifically as we sort of have an eye towards LSST turning on. All right, so in conclusion, the 15-year data set has evidence for a correlated stochastic gravitational wave signal. That signal is sort of follows the expected cross correlation signature for a gravitational wave background. There's continue to be a lot of potential sources. Our spectral characterization will continue to improve. And I think one of the things that's really cool is to see that there is consistency in this signal across all pulsar timing array collaborations. And so we are in the process of combining all of our data under the International Pulsar Timing Array, and we will be analyzing that combined data set in the coming few years. It has way more pulsars and a way longer baseline than any individual PTA data set, and so it'll be very exciting to see what we find in there. Apologies for the technical issues, apologies for going over, but thank you all so much for sticking with us, and we would love to answer any of your questions.
Thank you very much, Javi and Joe, for the great presentation. We have a few minutes for question and answer session. So if you have any questions, feel free to raise your virtual hand or write your questions on chat. Right now, I don't see any. Oh, Satya has a question. Satya, go ahead and unmute yourself and ask a question.
Thanks a lot, guys, and congratulations, first of all, on this very impressive, as you call it, evidence for nanohertz gravitational waves. I wanted to ask you about the SMBVH model. You say it is consistent. You had a model in which you varied the mass distribution and interaction and all that. But when you look at your favorite model or anywhere over the parameter space, you got a number density. Is that number density of supermassive black holes? What is it? Do you have a number for it? And is that consistent with what normally astronomers say the number density of, I don't know what the number density of binary black holes is, by the way. That may be hard. That's the difficulty, because it's a small number statistic. There are only a handful. And I wanted to also ask about the OJ something. Where does that sit in your parameter space? Thank you.
Absolutely, yeah. So it's a great question. And so I don't have the slide available here, but if you look in the paper where we assume binary supermassive black holes, one of the things that you'll find is that the background is really dominated by a biased sample of the entire population, right? Most of the electromagnetic observations for the binary supermassive black hole population are probing things that are at lower masses than what we're probing, right? So there's a huge amount of uncertainty in that high-end mass tail. So we are absolutely consistent with that, but that's more about how uncertain and unconstrained that is. So in particular, there's just not a lot of very good constraints on massive black holes at high redshift.
That is correct. That's correct. Yeah. But the question is also, are you then able to constrain the density better than what astronomers know? And finally, is that number density consistent with the fact that you don't find anything in individual binary? in the nearby universe with your own analysis?
Yes, so it is consistent. There's a recent paper that I'm not sure if it's on the archive or it'll be on the archive soon. That's sort of looking at individual mass and individual system and anisotropy predictions based on the amplitude of the background that we currently see. And so things are certainly consistent.
Okay.
And and you asked about OJ287.
Yes.
OJ287 is a little bit it is under our sensitivity curve at the moment. It's a little bit, the mass ratio is a little small, and the mass of the primary is a bit small. There are some targeted searches for it that are ongoing in the data. I should say that almost all of our models are assuming circular binaries. And of course, OJ287 has some amount of eccentricity. So searching for eccentric systems is a little bit more complicated, but there are searches ongoing to put some constraints on that system.
Thank you.
Yeah.
Congratulations once again.
Thanks.
Raymond?
Oh, yeah, thanks, guys. A naive question. You mentioned LSST. How is Vera Rubin going to help you? I don't quite get that.
Oh, yes. Sorry. I was specifically talking about targeted searches for binary black hole candidates. And so Vera Rubin is going to have hundreds or thousands of candidates based on AGN optical light curve variability. A handful of those will be massive enough that we will be able to place some amount of a constraint. And so there's a real sort of synergy. Certainly, a lot of those are going to be false positives. We don't have a good sort of intrinsic noise model for AGN variability. That's a thing that LSST will definitely help with. And so PTAs will have some say in terms of distinguishing and placing some constraints on a few of those systems.
Thanks.
Yeah.
Can I quickly make a comment? Because I asked Steve Taylor, he was here, and I was talking to him about precisely this issue, and he did not think the targeted searches will help the sensitivity anyway. It will give you targets maybe, but it may not help the sensitivity. Is that correct?
Well, if Steve said it, it probably is. But
if there is a paper, I would like to know. That's
yeah, no, certainly. So there was a targeted search of 3C66b led by Caitlin Witt. And one of the things that we found in that analysis is that certainly as you reduce the volume of the frequency space that you search over, your ability to place constraints on the masses of the systems improves. Now, I don't have a good sense of what the frequency constraints that will be coming out of LSST are, and so it certainly could be that that just the information isn't going to be constraining enough to actually to increase PTA sensitivity. So that's certainly an assumption.
Yeah. Sorry about interjecting. Sorry.
No.
Thank you.
Yeah.
Ryan?
Yeah. Hi. Thank you for the great presentation. I just had a quick question. Towards the end, you mentioned that in the future you'll be looking at the international PTA. And I'm wondering if that has already started, or if not, when that would start.
Yeah, it's a great question. So the process of combining all of the data is really complicated. You're talking, in Nanograph, we have, basically 2 or 3 telescopes. When you talk about combining through the entire IPTA, you're talking about a dozen telescopes, and they have different back ends, and so combining all of that is not a trivial process. So the data combination is already happening. There's a preliminary combination of, I think, half a dozen pulsars that should be done relatively soon, that will start to be able to test our analysis pipelines on, and we expect a full data combination, I think by the end of next year, plus or minus 6 months.
Okay, thank you very much.
Yeah.
Okay, let me think. Have enjoyed again for the great presentations, and I thought they were very accessible to non-experts like me, so I really appreciate it. Yeah, thank you everyone for attending today. And as Alejandro already announced, the next DGraph seminar is on November 2nd by Samgrada and Honji Wei at University of Arizona. So I hope to see all of you in 1 month. Okay, thank you. And
Thanks, everyone.
Thanks, everyone.
Thank you, Ken. Bye-bye.
yeah, thanks, Alejandro.